Here's answers to the bonding test free response. The first one was on a compound called tetrafluorohydrazine, which is used as a rocket fuel. We just wanted to draw the electron dot structure of N2F4 so that the nitrogen atoms are sp3 hybridized. Now, sp3 hybridized just really means that there's going to be 4 electron groups around each nitrogen. You can get the right structure by simply connecting the dots. This is kind of old school, where nitrogen has 5 valence electrons, which I kind of showed in red. There would be 3 singles and 1 lone pair on the nitrogen. Then typically nitrogen would be looking to make 3 bonds, so we can connect once to the other nitrogen, and then the other 2 bonds can go to the fluorine on the outside. That should give me an sp3 hybridized nitrogen, really just meaning that there are 4 electron groups on the nitrogen. Now, common wrong answers might be like this one with a double bond in the middle, and I get it. Like, this one is a legit structure. It follows the octet rule and all that. If you were to use formal charge, this one doesn't end up being the best structure. That single bond in the middle with the lone pair ends up being the best by formal charge, which is probably why they wanted us to draw that version. If you do a double bond in the middle, you'd only end up with 3 electron groups on your nitrogen, which would be sp2. The other common wrong answer that I see is like, for some reason, a triple bond in the middle, which, yeah, nitrogen does typically triple bond, but then you can't also put 2 single bonds on a nitrogen because now you've overloaded your nitrogen. It can only take 8 valence electrons being in the second energy level. So if you go a triple and 2 singles, now you've got 2, 4, 6, 8, 10 electrons on your nitrogen, which is too many. In part B, you might be familiar with the Lewis structures of nitrogen and fluorine. If not, maybe you sketched them out and you had a single bond for your fluorine and a triple bond for your diatomic nitrogen. We want to use the bond energies given to calculate the energy change for the synthesis of 1 mole of the N2F4. And so we got to do bonds broken versus bonds formed. We add up all the energy required to break the bonds of the reactants. I got to make sure I get that 2 moles of fluorine single bonds. That's going to be positive endothermic. I have to add energy to break apart the reactants. We kind of do the same thing on the products, and this was based on the structure that you drew. So if you drew the structure wrong, you would have lost the point on the structure. But then let's say you did use a nitrogen-nitrogen double bond, you would have gotten the point for part B as long as you showed your work and you did it correctly. So there should have been single bonded nitrogen and 4 single bonded nitrogen fluorines. That gives me 1,248 kilojoules, but that needs to be negative or exothermic. Energy is released when the new bonds form. So overall, the energy change is the sum of these 2 processes. 1 endothermic positive. I have to add energy to break apart my reactants, and then I release energy when my products are formed. On the product side, it's negative, exothermic. Overall, we end up with a net gain of 1 kilojoule. How weird is that? Endothermic by 1 kilojoule. Takes just a little bit more energy to break apart the reactants compared to the energy I get released when the products form. There were 2 versions of Part C. Students drew inaccurate graphs trying to show the potential energy of the diatomic fluorine and the diatomic nitrogen. In this one, we've got the nitrogen with a lower potential energy, more energy released when the bond forms, which also means that more energy would be needed to break the bond, and that seems legit. Yeah, it's a triple bond. They're really strong, so they're going to release a lot when they form. I'm going to have to add almost 1,000 kilojoules to break apart that nitrogen triple, a mole of nitrogen triple bonds. Okay, so that's right. that the nitrogen should be at a lower potential energy level. However, that triple bond is also going to pull the atoms closer to each other. When you start overlapping those unhybridized p orbitals to make pi bonds, when you have doubles and triples, the atoms are going to be closer to each other. So I really should have a shorter internuclear distance between the nitrogen-nitrogen atoms. Now this is also pretty legit because if you look on the periodic table, nitrogen and fluorine are going to have a very similar radius. I mean, they're both in the second energy level, and yeah, maybe nitrogen has a couple extra protons and electrons, but their atomic radii are really similar. But that triple bond is a really strong bond. I mean, look at how much energy is released. And those guys then should have a shorter bond length. So maybe kind of like those red graphs that I drew. I mean, maybe that's a little bit exaggerated, but the bond length for the nitrogen-nitrogen should be shorter or farther to the left, and that single bond should be a little longer bond length or somewhere farther to the right. The other wrong graph was this one. Now this one we've got the opposite issue. The bond lengths are fine. The nitrogen-nitrogen triple should be a shorter bond length, so that one's maybe around 100 picometers, whereas the fluorine-fluorine is maybe around 300 picometers. Yep, that's a single bond, so it should have a longer bond length. But now the error is in the bond energies. That triple should release more when it forms and require more to break. So maybe kind of like these blue graphs that I have drawn on the bottom. And part D, NO2 is another compound used in rocket fuel. The NO2 molecule shown on the left has an odd number of electrons. Every now and then it can happen. It doesn't necessarily mean the particle is stable. So it can be converted to a more stable ion, NO2+. Yeah, we would like to get rid of that one random electron. In the box on the right, we want to complete the Lewis diagram for NO2+, showing all bonding and non-bonding electrons. Now, a couple errors that occurred were usually that people just didn't get the right electron count. So the nitrogen has 5 valence electrons, the oxygen each have 6, which gives you a total of 17. But then that +1 charge means you're going to lose an electron. So often people added an electron and then they drew a structure with 18 rather than 16. So we got to distribute 16 electrons so that everybody gets a full octet. And we have to have octets. Nitrogen and oxygen are only in the second energy level, and we don't have d orbitals available. So the best structure would be 2 double bonds around the nitrogen, and then we got to put our lone pair on the oxygen. 2, 4, 6, 8, 10, 12, 14, 16, and everybody gets an octet. And then finally, question 2 gave you a whole bunch of structures with selenium. In part A, we want to use formal charge to explain which version, A or B, is more stable. Now, number 1, you had to use formal charge. This wasn't about electronegativity or anything like that, or shapes or angles. Formal charge. Now, whether you showed your formal charges on the structure or you put them like in your answer, either is fine. Formal charge has to be done for every atom in the compound. You take the normal number of valence electrons and subtract the number assigned. Bonding pairs of electrons get split 50-50 between the 2 atoms in the bond, and lone pairs count just for that particular atom. So in this case, we would say structure B is better. It is a neutral compound, so all the formal charges should add up to 0, but we'd like more zeros for formal charges. That means that you assigned the number of electrons that the atom would normally carry. Now, if we would have any negative formal charge, we would want that on the more electronegative element, which would be the fluorine. But in this case, having all zeros is really the best option. So something about structure B being the best, all the formal charges are 0. Structures A A and B, for that matter, are both tetrahedrons. A and B both have 4 total electron groups around the center. It doesn't matter if they're single bonds, double bonds, triple bonds. It doesn't matter if the atoms on the outside are the same or different. Both structures A and B have a total of 4 electron regions around the center. They'll be tetrahedral with 109.5 degree angles. In C, the selenium-fluorine bond should be more polar. Both bonds are polar. The fluorine and the chlorine have a higher electronegativity than selenium, but fluorine is even higher than chlorine. So that fluorine is really going to tug on the electrons and make that bond more polar. So the partial positives and partial negatives will just be a little more extreme in the selenium-fluorine bond. That's where we're going to talk about electronegativity, when we're looking at polarity, bond polarity, or molecular polarity. Finally, D, the selenium-oxygen-chlorine molecule in diagram D has a dipole moment. Just a fancy word of saying that it's an overall polar molecule, meaning there will be regions of positive and negative charge. Dipole, 2 regions of charge. They want us to explain how its molecular geometry and bond polarity result in the dipole moment. And so we got to address both molecular geometry and bond polarity. So maybe first the geometry. In structure D, you've got, if I go back to D, 3 bonds and a lone pair. Okay, it doesn't matter that one of the bonds is a double. I've got 3 bonds and 1 lone pair, a total of 4 electron regions around that central atom. Makes me think tetrahedron, but 1 spots the lone pair. So it's going to be the trigonal pyramid. Now the trigonal pyramid is not the trigonal planar. This thing does not have nice symmetrical, evenly distributed angles around the center, because of that lone pair adding another region of charge. If I had a flat triangle with beautiful 120 degree angles, now even though I have polar bonds, if they're arranged evenly around the center, polar bonds can cancel. For example, if the structure looked like this, trigonal planar, now my polar bonds could be arranged at equal angles and they might cancel, as long as those outer atoms are the same. Well, that's not what we have here. We do not have the flat triangle, we've got the pyramid. So now we've got these polar bonds around the outside, but they are not arranged equally around the center. And so the chlorine and oxygen on the outside will have a higher electronegativity. So you're going to get some poles and some poles and some poles, but there's nothing up on top to offset that pole. And maybe you said something about how the atoms on the outside are also not the same. I've got 2 chlorine and an oxygen, where the oxygen might pull even more than the chlorine, because the oxygen has a higher electronegativity. But we are mainly looking for the fact that this trigonal pyramid shape is not going to give me a nice symmetrical distribution of atoms around the center. So because my bonds are polar, those bond polarities will not cancel, and I'm going to get regions of charge.